So on this video, we want to take a look at graphing conic sections again, back to from first semester. But there's something different about these conic sections. These conic sections are going to have an XY term, and we haven't dealt with an XY term at all. And the problem with the XY term is that algebraically, it causes some issues. Because when we look at conic sections, one of the common things we like to do is complete the square. And when you complete the square, you could combine x squareds with x's, and you could combine y squareds with y's. You kind of can't do anything with an xy term. So it's kind of like our Achilles heel, right? It's a thorn in our side. How do we eliminate that xy term? And the thing is we can't. We can't change the equation, but we can change the way we look at the equation. And so what the first video here that I'm posting is that we're going to look at, well, how can we maybe change how we measure that coordinate? So down in example one, I've got your traditional XY axes. And in my screen, it's dark black. So this point right here, this random point x comma y, means that if I go over x and up y, I can geographically get to that spot. And if I wanted to create a right triangle, this distance, which on my diagram is called r, kind of like the radius, right? I would know lots of things like x squared plus y squared equals r squared, and as well as other right triangle trig, identities. Now, if I could somehow rotate, and if I could somehow come up with a different axis, a different way to measure a vertical and a horizontal distance. And so that's sort of where this new axis comes into play. I printed out, it's like x hat, y hat. I'm gonna call them like x primes and y primes to indicate it's the same geographic point, but now your x prime is in this new direction. So I don't really know, I haven't identified what theta is yet, but if I measure it in this direction, so maybe I'll pick green here. So this distance here becomes my x prime, and then this distance here along the rotated axis is my y prime. But notice it's still, right, r away. So depending on which system, it's the same point geographically. It's just, is your vertical and horizontal your traditional xy axes? Or if you look at it slightly rotated, is that a better way to find maybe that line of symmetry to algebraically eliminate the xy term? And that's exactly what we're trying to do here. So let's look at this upper triangle here, because again, it's a right triangle. And I don't know, like this angle here, it's different than theta, but I'll just call it alpha for now. But I know a lot of things about that yellow triangle. I know that the cosine of alpha, I know that I can't write. I know that the cosine of alpha in this yellow triangle is x prime over r, which means that if I multiply the r across, anytime I have an r cosine of alpha, I know that's equal to x prime. And in a similar vein, I could say that sine of alpha is equal to y prime over r. Again, I'm just using SOHCAHTOA, so r sine of alpha is equal to y prime. So I'm going to keep track of these, and I'm going to do something very similar in the other triangle. So I guess I can go to orange here, maybe, and go a little bit thicker. So in this orange triangle, okay, so same idea, but now my angle here is theta plus alpha. So let's take a look. I could say, okay, cosine of the quantity, theta plus alpha. But now I'm in the normal, right? So I'm in the x over r, which means r cosine of theta plus alpha is equal to x. And we could do a similar expression, sine of theta plus alpha equals y over r. So r sine of theta plus alpha is equal to y. So let's expand, right? I know that, that's exactly what you're thinking, So I'm going to expand that using our cosine sine formulas. So let's come over this way. So we know that our cosine of theta cosine of alpha, and we do minus our sine of theta sine of alpha is equal to x. And then when we expand this one, we get our sine of alpha cosine, sorry, sine of theta cosine alpha plus r sine of alpha and cosine of theta equals y. And again, remember, we already know when we see an r cosine of alpha, we're going to replace it with x prime. So right there, there's an x prime with that cosine of x, sorry, cosine of theta, and an r sine of alpha is equal to y prime. So y prime sine of theta is equal to x. And then here's another r cosine of alpha, so that's an x prime sine of alpha plus, and here we'll get a y prime cosine of theta. I think I accidentally said alpha, but I meant to say theta. Okay, so if I could write this, I promise you I'm trying to write y equals, there it is. Okay, so that's really the punchline, that if you want to rewrite x and y in terms of some new rotated system, x prime, y prime, these are your translation formulas. So things that I just put in red, these are two of the three formulas you have to have memorized. Now, I'm all about patterns, and these just come from our cosine sine like functions. If you think about x being cosine, this is like co minus sine sine, right? And this one again, cosine sine co. So it just comes right from that. But these are the transformation formulas that you need. So, so I'm going to take those and take a look at example 2, and it's kind of like a baby step into doing what we need to do. I'm telling you this hyperbola, which is x times y equals 1, and we know this graph because last semester we looked at it as the reciprocal function, like y equals 1 over x. So we never really looked at it as xy equals 1. But technically, this is a hyperbola. And I'm claiming that if you rotate the axes by 45 degrees, like that's the perfect amount to create a hyperbola in that new rotated direction with a new set of coordinates. So instead of calling them x's and y's, we're going to call them x primes and y primes. So I'm going to take these two translation formulas that we just derived, and I'm going to apply them to the original, to the original equation, x times y equals 1, xy equals 1. So so this x, there's only one to change, but that x is going to be replaced with x prime cosine theta, x prime cosine theta minus y prime sine theta. And then the y value is going to be replaced with x prime sine theta plus y prime cosine theta. Okay, so again, I'm claiming that and I know it's 45 degrees, so that's what I really should do. My bad. So that means x prime cosine of 45 degrees, or pi fourths, minus y prime sine of pi fourths, and then x prime sine of pi fourths plus y prime cosine of pi fourths. So I claim that 45 degrees is the perfect angle to get rid of the xy term. So let's do it. And we know what the cosine of pi fourths is. It's root 2 over 2, which is the same as sine. So this is root 2 over 2 x prime minus root 2 over 2 y prime. And this is also root 2 over 2 x prime plus root 2 over 2 y prime. So that equals 1. So let's multiply. So when we start multiplying things together, right, so this times this, so that's root 2 times root 2, which is 2 over 4. So we get 2 over 4 x prime as a term. We got to be careful here, squared, because I don't want to look like the 12th power. And then we take this term times this term. So that's plus 2/4 x prime y prime. But then look at here, minus 2/4 x prime y prime. That's fantastic. Notice these are going to cancel. And then our last two terms, minus 2/4 y prime as a quantity squared equals 1. And as promised, these middle terms cancel. The x prime, y prime terms cancel. So when I rewrite this very nicely, it's going to be 1/2 x prime squared minus 1/2 y prime squared equals 1. Now, at some point, it gets a bit tedious to keep writing prime, 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 prime. So eventually you can say, okay, in the new system, in the translated system, once we know we're in the new system, I could recall it x squared over 2 minus y squared over 2 is equal to 1. And I'll rewrite that in, like I shouldn't say translated, in rotated system. In rotated system. Okay, and this is characteristic of a hyperbola, right? It's a difference of quadratics. We set equal to 1. We know it's a hyperbola, which is fantastic. Okay, so the thing I guess the elephant in the room is I told you 45 degrees. So these formulas, right? These formulas only work, right? Up here, these formulas only work if you know that angle. If I don't tell you the angle, or if you don't know the angle, then you can't simplify. So the next video is going to develop and improve how do you know the angle if it's something that just has an arbitrary xy term. So first video done, and we'll take a look at video number 2.